Okay, thank you very much for your kind invitation to share our results about this real scale test on Rockfalls. I will be talking myself. I am Josep or José Gili, Gili, but I will talk on behalf of my group of colleagues. We are a team working on natural hazards and landslides and monitoring and engineering geology in Barcelona at the UPC. Here you have most of the team that are participating in the several ongoing projects. Most of them are funded by the National Research Institution. My talk is the third one, but I think it is quite related with the last one by Ferdinando. It has been very interesting, and I think that is very nice to share the results between the groups that are close, more or less, in the mathematical part, in the physical procedure, and also in the labs. When Frank get in contact with me, he talked about analog field lab. That's wonderful. That's a nice concept, and I think that sometimes, or from time to time, it is necessary. It's very important to going outside to the real world in order to test, to touch the real thing at the real scale. In principle, or the main part of my presentation corresponds to this paper. This is a last year paper, 2022, that appears in Landslide. That is a well-known journal in our field. Don't miss, if you have time or you have interest, don't miss the electronic supplementary material that is attached to this paper. Why we conduct this set of experiments? This is why we were doing simulations of the rockfall propagation. I mean the trajectories, and we combined these simulations with field observations, and we realized that the fragmentation of the initial blocks, or the initial rock blocks or masses, was of paramount importance in order to explain the final result. Because if you take into account the fragmentation or not, you will get completely different results. For this, we envisage some test that I will present right now. Here we have an example of what I was saying. This is in the paper of Matas et al. Here we have in red the simulation of a single block, 100 cubic meters block downhill from a cliff here in the upper part to here in the valley. If we simulate the one block keeping unfragmented, we reach this point here. But on the other side, if we take into account the fragmentation with average parameters, we get the most of the fragments, hundreds of fragments, thousands of fragments will be stopped at the middle part of the slope. That corresponds much better with the real thing, because here we can see that in this cliff, in the bottom part of this cliff, we have a huge amount of blocks that has been stopped due to past events. Here in the right, the same thing. If we take into account or not the fragmentation. In the left, we have the one single event, and in the right, we have hundreds of simulations for taking into account the a simulation of hundreds of blocks. You can see that if we take into account the fragmentation in the right, the blocks keep closer to the middle part of the slope, but if we do not take into account the fragmentation, the blocks reach in a very much extent, in a higher extent, the bottom part of the valley, that this is not the real case. What happens if we take into account the fragmentation, the individual energy of a single fragment is lower, but we have a huge number of fragments, so the probability of impact to a vehicle, a car, a building, a people that is walking in the area is higher with fragmentation. So we take the conclusion that we have to take into account the fragmentation. The two lines of work in the project that we started in 2015 were natural fragmental rockfall inventories around the mountain, mainly in the Pyrenees, and also to take into to carry out the rockfall fragmentation test. We carried out 4 of these real scale tests in several open pit mines around close to Barcelona. Here we have the profiles or the perspectives of these 4 sites. 3 were on limestone and 1 was on granite. This is the general setup of the thing. The tests were started with the preparation of the blocks. Here we have the painting of the blocks. We made photogrammetry survey for each block, and we make multiple measures on each block for joint characterization purposes. Here another picture about the preparation, and another picture of the joint characterization. With this 3D photogrammetric survey, we get this 3D model that can be inspected later on in order to make further measurements and further studies. We can have this model even in the case of the block has disappeared, has been fragmented during the drop. Here we have the real sense or the purpose of the painting of the 3 big circles in red, yellow, and green. This is to easy the task of identification of the center of masses of each block during the trajectory downhill in each test. As you can see, we got the high resolution and high velocity videos from 3 different points around the slope. In this way, we were able to reconstruct the trajectory meter by meter. This is a general view of the first of the test sites. In abstract or in summarizing, we drop 124 blocks ranging up to 5 meters. And we were able to record as much as 200 impacts with or without fragmentation. This is a detail of the drop. Here we can see a detail of the blocks in the floor in the explanade downhill, where the blocks and the fragments were measured one by one in order to have the final volumes and number of fragments. Here I have some videos I want to share with you. The first one is this one. We can, first of all, we see the general aspect of the test number 4 site with the dozer in the top of the slope, the main plane here, and the several cameras in the lower part. And here we can appreciate several of the drops at real velocity. Here we have some drops at slow motion, and we can see the detail of the thing. This one's from one camera. Here some close-up views of the blocks when impact with the slope, and we can appreciate the fragmentation. Studying these blocks, we were able later to study the patterns of the fragmentation and to derive some relations between the initial shape, the number of fragments, the energy, the impact angle, and so on. This is block number 5, as you can see. And we got up to 200 of these events. In global, we were able to derive some relations between the angle, the height, the energy, the shape of the block, and the impact mode. Some of these videos has also sound, but now I am displaying it at mute in order to keep the micro open. The fragmentation take place in the slope or in the explanade, depending on the site and depending also on the block. Okay, let me stop the videos because I am finishing the time. With the data obtained, we were able to study the accumulated block size distribution. These are some of the results that we got after the test with a lot of post-processing and analyze. This kind of curves are very interesting in the simulation in order to introduce realistic behaviors in the propagation and in the fragmentation. We were also able to study the trajectories, the first block trajectory and later on the fragments trajectories, the velocities, the accelerations, angles, and so on. At the first try, we get no correlations between some variables, but later on with eventual additional work, we were able to obtain some nice correlation or good correlation between brackets between the fragmentation and no fragmentation events, and the groups of parameters or the parameters grouped in order to have some fully physical variables with physical sense. In this example, this last picture is the one that can be obtained, can be studied in the paper in landslides. A final video to show one of the objectives of the study on fragmentation. Our code, Rock.js, improved after the real scale tests, is used to simulate the trajectories and energy of 21 blocks under fragments. Let me say that finally, I have to acknowledge the Ministerio de Ciencia e Innovación for funding. Here in the bottom you have the three subsequent projects that we have had in this line of work: rock risk, rock models, and georisk. Here you have some related papers in this subject. Thank you very much for your attention.